The function f of x equals 2 to the x is called an exponential function because the variable x appears in the exponent. This type of function should not be confused with the power function g of x equals x squared, where the variable x appears in the base. The exponential function 2 to the x can be understood for integer values of x fairly easily. For example, if x equals 4, then 2 to the 4 means the number obtained by multiplying 2 with itself 4 times, which is 16. If the exponent is negative, then we just take the reciprocal. For example, 2 to the negative 4 is just 1 over 2 to the 4, or 1 over 16. It's also not too difficult to make sense of rational exponents, that is, exponents that are fractions of integers. For example, 2 to the 5/3 means the third root of 2 to the 5th power, or, equivalently, the 5th power of the third root of 2. In all of these computations, the rules of exponents apply. Two important rules include 2 to the x times 2 to the y equals 2 to the x plus y, and 2 to the x all raised to the y equals 2 to the xy. Irrational exponents, such as the number pi, can be understood too using a type of approximation process, but we won't go into all the details about that here. The important thing is just that the exponential function 2 to the x is defined for all real numbers in this way. In other words, its domain is the entire number line. The graph of this exponential function is indicated here by this curve with increasingly steeper slope as we move to the right. This increasing steepness indicates that the curve grows very, very fast, much faster than any power function or any polynomial. The point 1, 2 lives on the graph because when x equals 1, the value of the function is 2 to the 1, or 2. The point 0, 1 also lives on the graph because 2 to the 0 equals 1. In fact, for any base b, we have that b to the 0 equals 1, so the point 0, 1 always lives on the graph of any exponential function. For example, the graph of the exponential function 3 to the x is similar to the graph of 2 to the x in that it passes through the point 0, 1, but 3 to the x now has the value of 3 at the point x equals 1. Comparing these graphs, we see that at the y-intercept, that is, at the point 0, 1, the slope of 3 to the x must be steeper than the slope of 2 to the x. At present, it's not entirely clear what's meant by the term slope for a curve, so this statement about comparing slopes of curves can't be made entirely rigorous, at least so far. In fact, one of the goals of this course is to understand what is meant by such a slope, and we'll cover this later on. For our current purposes, it's sufficient to think of this slope as being equal to the slope of a line that is tangent to the curve at that given point. That is, a line that touches the curve only at that given point. With this understanding of slope then, we're able to compare the slopes of 2 to the x and 3 to the x at the y-intercept. But what about the slopes for other bases? Well, since the base of 3 produced a steeper slope than that of 2, it seems natural to guess that the size of a base determines the size of the slope at the y-intercept. This indeed turns out to be true. For example, the slope of 4 to the x is even steeper than that of 3 to the x. As a special situation, the slope of the exponential function with base equal to 1 is actually 0, because its graph is a straight line, since 1 to the x equals 1 for any value of x. It's also possible for the slope to be negative. For example, the graph of the exponential function with base equal to 1/2 is just the reflection of the graph of 2 to the x, and so its slope at the y-intercept is equal to negative that of 2 to the x. There's a particularly special base that proves useful in this course, namely, the base where the slope at the y-intercept is exactly equal to 1. This number, lying between 2 and 3, is denoted by e for the mathematician Euler, credited with its discovery. Its value, correct to 5 decimal places, is 2.71828, and so on. Like the number pi, the exact value for e is an endless non-repeating decimal, which is irrational, meaning that it cannot be expressed as a fraction of two integers. The number e is also sometimes called the natural number, and the corresponding exponential function is also called the natural exponential function.